This is an absorption chiller. There's no compressor in it. There's no motor, and in one version of it, there are no moving parts whatsoever, not a single one. You apply heat at one end, and cold comes out the other. That is the entire machine, and versions of it are running right now in RVs, hotel rooms, hospitals, and university campuses across the country. And here's the honest part stated up front, because almost nobody covering this will say it. Per unit of energy consumed, this is less efficient than the air conditioner you already own, substantially less. Anyone telling you it is a free upgrade has not run the numbers. But that comparison misses the entire point, and once you see why, this becomes one of the most genuinely useful machines in this whole field. Because an ordinary air conditioner runs on electricity, which is the most expensive energy you can buy. And this machine runs on heat, which is very often the cheapest thing you have or free waste you are currently throwing away. Stay with me, because that single trade explains why hospitals use these, why every RV has one, and why they nearly disappeared from ordinary houses. Let me start with how cooling actually works, because almost everybody has the mechanism backwards. Nothing makes cold. Cold is not a substance, and it cannot be manufactured. Every refrigerator and every air conditioner on Earth is a heat pump, meaning a machine that moves heat from where you do not want it to somewhere you do not care about it. The trick they all use is evaporation. When a liquid turns into a gas, it absorbs a large amount of heat from its surroundings, which is why alcohol on your skin feels cold and why sweating cools you down. So every cooling machine does four things in a loop. It evaporates a liquid inside your fridge or your house, which pulls heat out of that space. It then has to get that gas back into liquid form so it can do the job again, which means squeezing it and dumping the heat outside. That squeezing step is the whole problem, and it is where the money goes. In the air conditioner bolted to the side of your house, that squeezing is done by a mechanical compressor, driven by a large electric motor, and that motor is why the machine draws thousands of watts and why it dominates your summer bill. The compressor is not doing the cooling, it is just the pump that resets the cycle, which raises a question somebody asked in the 1800s. If the compressor is only there to move the refrigerant around, is there another way to move it that does not involve a motor? There is, and the answer is chemistry. Certain liquids will absorb certain gases enormously well. Ammonia gas dissolves into water with remarkable eagerness. Water vapor is absorbed by a lithium bromide solution the same way. So instead of squeezing the gas mechanically, you let it dissolve into a liquid. The gas disappears into solution, which does exactly what a compressor does, meaning it removes the low pressure vapor from your evaporator and lets more liquid evaporate. Then you take that solution, apply heat to it, and boil the gas back out under pressure. From that point, the cycle continues exactly like a conventional system. Engineers call the whole arrangement a thermal compressor, and it is genuinely one of the most elegant substitutions in engineering. You have replaced a motor and a compressor with a chemical solution and a flame. The machine has four parts. A generator, where heat drives the refrigerant vapor out of solution. A condenser, where that vapor turns back into liquid and dumps heat outside. An evaporator, where the liquid evaporates and produces your cooling. And an absorber, where the vapor dissolves back into the solution to begin again. Heat in at one end, cold out at the other. No compressor anywhere in the drawing. There are two chemical pairings that dominate, and knowing which is which tells you immediately what a machine can and cannot do. The first is ammonia and water, where ammonia is the refrigerant and water is the absorbent. Ammonia boils at around minus 33 degrees Celsius at atmospheric pressure, which means this pairing can produce genuine freezing temperatures. That is why every RV fridge and every off-grid freezer built this way uses ammonia, and it is also why those systems carry a toxic chemical under pressure. The second is water and lithium bromide, where the water itself is the refrigerant, and the lithium bromide solution is the absorbent. This pairing is non-toxic and non-flammable, which makes it ideal for large buildings full of people. But it has one hard limit that shapes its entire application. The refrigerant is water, and water freezes, so these machines cannot produce temperatures below zero. They are excellent for air conditioning, where you only need chilled water at 5 or 10 degrees, and completely useless for a freezer. So the split in the industry is clean. Ammonia for cold and for small off-grid units. Lithium bromide for large-scale air conditioning in occupied buildings. If you see a chiller the size of a truck in a hospital basement, it is almost certainly lithium bromide. If you see a fridge in a caravan, it is ammonia. Now, this is not new, and the history here is far better than the technology deserves. In 1858, a French engineer named Ferdinand Carré patented an ammonia water absorption refrigeration machine, and it worked well enough to produce ice commercially. And that timing turned out to matter enormously because of what happened 3 years later. During the American Civil War, the Union blockade cut the Confederate States off from the northern ice trade, which until then had shipped natural pond ice south by the boatload. Cities that had depended on it for food preservation and for hospitals suddenly had none. Carré machines were brought in, and absorption ice plants operated in the South during and after the war. producing ice with heat instead of winter. Think about that sequence. A blockade cut off the supply of cold, so engineers built machines that made ice out of fire. The technology then had a second stranger chapter in the 1920s. In Sweden, two students named Baltzar von Platen and Karl Munters developed a version with a genuinely remarkable property. By adding hydrogen gas to the ammonia and water, they created a design that circulated entirely on its own through heat and gravity with no pump and no moving parts at all. Not a quiet motor, not a small motor, none. The way they achieved that is worth understanding because it is the cleverest part of the whole story. A conventional absorption system still needs one small pump to move the enriched solution from the absorber back up to the generator against pressure. Platen and Munters removed even that. They did it by adding a third substance, hydrogen gas, and running the entire machine at a single uniform pressure throughout. Since there is no pressure difference between the sections, nothing needs pumping against it. Instead, what changes from section to section is the partial pressure of the ammonia, meaning how much of the gas mixture is ammonia versus hydrogen. In the evaporator, the ammonia is diluted by hydrogen, which lets it evaporate at low temperature and produce cold. In the absorber, the ammonia is stripped back out into the water and the hydrogen is left behind to circulate again. The fluids move on their own, driven by heat and by gravity, in a closed loop of welded steel tubing with no valve, no seal, and no shaft anywhere in it. That is why an RV fridge is silent, why it lasts for decades, and why there's genuinely nothing inside it that can wear out. The only thing that can fail is the metal itself, either by corrosion or by the solution crystallizing if the unit is run badly tilted. Engineers call it the diffusion absorption refrigerator, and it is one of the very few machines in daily use that has no moving component of any kind. That design was picked up commercially and became the Electrolux absorption refrigerator, and its direct descendants are in essentially every RV and caravan sold today, and then the chapter almost nobody knows about. In 1930, Albert Einstein and his former student Leo Szilard were granted a United States patent for an absorption refrigerator of their own design. The reason they built it is the part worth remembering. Reports at the time described a family killed in their home by a refrigerant leak caused by a failed seal on a mechanical refrigerator, at a time when the refrigerants in use were toxic gases like sulfur dioxide and methyl chloride. Einstein and Szilard concluded that the answer was a machine with no seals to fail because it had no moving parts, and they patented one. Their design never reached the market, and the reason is the reason this entire technology retreated. Freon arrived. Through the 1930s, chemically stable, non-toxic refrigerants were developed for vapor compression systems, which eliminated the safety problem that motivated Einstein's design in the first place. At the same time, electric motors became cheap, reliable, and small, and household electricity spread across the developed world. So the compressor won, decisively and fairly. It is more efficient per unit of energy, it is compact, it works instantly, and once electricity was cheap and refrigerants were safe, there was no reason for an ordinary household to own a machine driven by a flame. Absorption cooling did not fail. It lost to a better answer for the specific case of a house connected to a grid, and it retreated to exactly the places where that case does not apply, which is where it still is, and it is worth seeing at 4 separate scales. Start with the RV, because millions of people own one of these without knowing what it is. The fridge in a caravan or motorhome very often has no compressor. It is a Platen Munters absorption unit, and it runs on a small propane flame. That is why it is silent, why it works with no electrical hookup at all, and why it can run for weeks in a field on a bottle of gas. Owners rarely think about it, and yet it is one of the most elegant machines they own. A flame at the bottom produces cold at the top, with nothing turning anywhere inside. Then the hotel minibar, which is the same technology in a different box. Absorption units are used there specifically because they are silent, and a compressor cycling on and off at 3 in the morning next to a bed is a complaint waiting to happen. Then the commercial scale, which is where the real money is. Large buildings across the country are cooled by lithium bromide absorption chillers in hospitals, universities, industrial plants, and district energy systems. The logic there is purely economic. Those facilities already produce enormous quantities of heat, whether from steam plants, from industrial processes, or from generators producing electricity on site. That waste heat used to go up a cooling tower and vanish. Feed it to an absorption chiller instead, and it produces air conditioning for effectively nothing from energy that was already being thrown away. Engineers call the combined arrangement trigeneration, meaning one fuel input producing electricity, heating, and cooling together, and it is standard practice in serious facility engineering. And then solar cooling, which is the version that ought to make you sit up. Consider the coincidence at the heart of it. The hotter and sunnier it is, the more cooling a building needs, and the more heat a solar thermal collector produces. Supply and demand peak on the same afternoon. So solar thermal collectors feeding an absorption chiller produce air conditioning driven directly by the sun that is causing the problem, with no photovoltaic panels and no batteries anywhere in the system. Installations of this exist, they work, and they are most common in hot sunny regions where the arithmetic is strongest. The practical catch with solar absorption is temperature rather than quantity. A single effect machine wants heat somewhere in the region of 80 to 100 degrees Celsius at the generator, which an ordinary flat plate collector struggles to reach reliably, and an evacuated tube collector delivers comfortably. That is why almost every serious solar cooling installation uses evacuated tubes rather than flat panels, and why the collector array is usually the largest single cost in the project. Double effect machines, which are more efficient, want considerably hotter input still, typically from steam or from a high temperature source, which puts them firmly in the commercial category rather than the backyard one. So the honest shape of a solar cooling project is that the chiller is the easy part and the heat supply is the expensive part, which is precisely the opposite of what most people assume when they first hear the idea. This channel exists for exactly this kind of straight answer. One honest method a week, and subscribing is how those keep arriving. Now the arithmetic, and this is the number that decides everything. Engineers rate cooling machines by coefficient of performance, meaning units of cooling delivered per unit of energy consumed. A modern vapor compression air conditioner achieves a coefficient of performance around 3 to 4. Put 1 unit of electricity in, get 3 or 4 units of cooling out, which sounds like magic, and is simply what a heat pump does. A single effect absorption chiller achieves around 0.7. A more sophisticated double effect machine reaches roughly 1.2. So on paper, absorption is 3 to 5 times worse. That is the honest number, and I'm not going to soften it. If you generate heat by burning fuel you paid for, purely to run an absorption chiller, you're wasting money compared to a normal air conditioner. But now change one thing. Make the heat free. If the heat is waste from a process you were running anyway, or from a generator already producing electricity, or from a solar collector on a roof, then the coefficient of performance comparison stops meaning anything at all because you are dividing by a cost of 0. Cooling produced from waste heat is cooling produced from nothing, and no compressor efficiency figure competes with nothing. That single insight is why every deployment I just described exists. Hospitals with steam plants, factories with process heat, RVs with a propane bottle and no grid, solar installations in hot climates. The rule is simple. If you are paying for the energy, buy a compressor. If the energy is already there and going to waste, absorption is close to free cooling, and there's nothing else that turns heat directly into cold. Now the $68 version, and I have to be careful here, because this is one of the few builds in this series I will actively tell you not to attempt from scratch. Ammonia absorption systems operate under significant pressure, and ammonia is toxic and corrosive. Building one from raw components involves welding pressure vessels and charging them with a hazardous refrigerant, and that is genuinely dangerous work for anyone without the right training and equipment. I'm not going to walk you through it, and you should not attempt it. The practical version is entirely different, and it is what people actually do. You buy a used absorption refrigerator, which is a sealed, factory-built, tested unit, and you repurpose it. Secondhand RV and caravan fridges appear constantly on marketplace listings, often from people upgrading a vehicle or breaking one up, and they commonly sell for $50 to $150, with the smaller camping units at the lower end. That is where the figure in the title comes from. What you're buying is a complete Plettenmunter system, factory sealed with no moving parts, that will run on a propane flame or heating element with no electrical connection required beyond ignition. For an off-grid cabin, a workshop, or a shelter with no power, that is a genuinely excellent piece of equipment, and it is the honest version of this build. A few things to check before you hand over money for a used one, since these are the failure modes. Smell it. Open it up and put your face near the cooling fins at the back. Any sharp chemical odor means the sealed system has leaked, and that unit is scrap. This is the single most important check, and it takes 5 seconds. Look for yellow staining or a fine yellow powder around the tubing at the back, which is the residue an ammonia leak leaves behind and is a definite reject. Ask how it was stored and transported, because a unit that spent a year lying on its side may have crystallized internally. Some units recover if you turn them upside down for a day and then set them upright, which is a genuinely standard trick among RV owners, but there's no guarantee. Check the burner area for heavy rust and for wasp nests in the flue, both of which are common in units that sat outside and both of which are fixable. And if you can, ask the seller to run it for an hour before you buy. Your working absorption unit will get noticeably warm at the back and cold inside within that time, and that single test tells you more than any amount of inspection. If you want to go further, the real project is the heat source rather than the chiller, meaning feeding an existing absorption unit from solar thermal collectors or from the waste heat of a generator instead of from bottled gas. That is a serious build, and it is where the interesting engineering actually sits. It is also worth being clear about what a single second-hand unit realistically does for you, since expectations are where these projects go wrong. An RV absorption fridge is a fridge, not an air conditioner. It will hold a food compartment cold and run a small freezer section on roughly a pound of propane a day depending on size and ambient temperature, indefinitely with no electricity. For an off-grid cabin, that is genuinely transformative because refrigeration is normally the single hardest load to cover. A fridge runs 24 hours a day, and covering it with solar and batteries means sizing an entire system around one appliance. Take that appliance off the electrical system entirely and hand it to a propane bottle, and the solar array you need shrinks dramatically. That is the real off-grid play here, and it is why absorption fridges remain standard equipment in cabins, boats, and remote installations long after they vanished from ordinary kitchens. Now, the section the sponsored videos skip, because this has real limits, and an honest account owes them the same volume as the praise. The first is efficiency, which I have given you and will not repeat, except to say that everything depends on whether your heat is free. The second is that these machines are bulky and heavy for the cooling they deliver, which is why they never suited cars or household kitchens in a world with cheap electricity. The third is level operation, and this catches RV owners constantly. An ammonia absorption unit relies on gravity to circulate its fluids, so running one significantly tilted disrupts the flow and can permanently damage the unit by allowing crystallization inside the tubes. They must be reasonably level. The fourth is startup time, since a machine driven by a flame takes hours to pull down to temperature rather than the minutes a compressor needs. The fifth is that they do not modulate well, meaning they run best at a steady heat input rather than cycling to match demand. And the sixth is repair. A sealed absorption unit that develops an internal leak or a crystallization blockage is generally not economically repairable, and that is the trade you accept in exchange for having no moving parts to wear out. Now the safety section, and this one genuinely matters more than most in this series. Ammonia is toxic and corrosive. A leaking unit produces a sharp, unmistakable smell, and it is an immediate reason to ventilate the space and leave. Never cut into, drill, or attempt to open a sealed ammonia unit under any circumstances, since it is a pressure vessel containing a hazardous chemical. Do not attempt to build an ammonia system from raw components. Buy a factory unit. If you run one on propane, remember that you have installed a combustion appliance. It needs proper ventilation, a correct flue arrangement if enclosed, and a carbon monoxide alarm in the space. This is not optional, and improperly vented absorption fridges have caused genuine harm in enclosed vehicles. Keep the unit reasonably level, keep the ventilation panels clear, and inspect the burner area for corrosion and blockage periodically. And if you ever smell ammonia around one, stop using it, ventilate, and dispose of it properly rather than trying to repair it. The ledger for the whole story then. A used RV or camping absorption fridge, $50 to $150. A propane bottle and regulator, $20 to $50 if you do not already have them. A carbon monoxide alarm, $15 to $30, and that one is not negotiable. If you want to drive it from solar thermal instead, collectors and plumbing take the project into the hundreds and turn it into a genuine engineering exercise. Here's the thing worth keeping from all of it. In 1858, a French engineer worked out how to make ice with fire, and within a few years, those machines were producing ice in a blockaded country that had lost its supply of winter. In 1922, two Swedish students removed every moving part from the design. In 1930, Albert Einstein put his name on a patent for one, because he had concluded that a machine with no seals could not leak and kill a family in their sleep. Then a safe refrigerant and a cheap electric motor arrived, and the whole line of thinking became unnecessary for anyone with a wall socket. It never stopped working. It simply lost the one comparison that mattered in a wired world and retreated to the places where nobody has a wall socket or where the heat is already there and going to waste. Which is worth remembering the next time you stand next to a running air conditioner in July and feel the hot air pouring off the back of it. That is the same energy this machine runs on, and almost every building on your street is throwing it away. And the scale of that waste is genuinely difficult to hold in your head once you start looking for it. Every power station, every factory, every generator, and every engine on Earth converts a minority of its fuel into useful work and rejects the rest as heat. Enormous quantities of it continuously into cooling towers and exhaust stacks in the air above car parks. Absorption cooling is one of the very few technologies that can take that rejected heat and turn it directly into something people want without converting it to electricity first. That is not a small idea. It is the reason serious facility engineers keep building these systems while ordinary homeowners have never heard the word absorption. And it is the clearest example in this entire series of a technology that is thriving in the places where the numbers are examined carefully and absent everywhere else. Everything this channel has gathered on cooling and heating a home the honest way, the loops, the stores, the real numbers, and the real limits, lives in one place, linked right below. And the comments are where this one gets interesting. Has anyone here run an RV fridge off-grid, and what did you actually think of it? And if you have ever seen an absorption chiller in a hospital or a plant, tell me, because most people have no idea those buildings are cooled by heat. As for the machine that produces cold at night by radiating heat straight into space, with no compressor, no fuel, and no moving parts at all, that is on screen right now. Same enemy, stranger physics. Till next time.